In the last class, we discussed on the equations for the transmission lines and input impedance of a transmission line which is connected with a load of ZL. So we have taken the simplified case of lossless lines and found the simplified equation for that. And from a knowledge of this, we try to understand what will be the use of the two types of transmission lines. That is, one is with a lambda by 4 length and the other one is a lambda by 2 length. That is half wave and quarter wave lines. What are their applications? And we have seen that they are very much used in all the ICs used at high frequencies. That is what they call as RF ICs, radio frequency integrated circuits. They use these transmission lines as inductors and capacitors or to realize the series and parallel resonant circuits. We know these series and parallel resonant circuits have many applications in almost all the types of filters and other tuning circuits. That is to tune an oscillator or to adjust the frequency response of an amplifier or to get very high gains from the amplifiers. We know we use these LC circuits, and similarly in LC circuits are also used along with the filters or the antennas and other things to improve the performance of these other types of circuits like antennas. That is, if the antenna output is very low, and to get the current output converted as voltage, we use a simple LC circuit and see that the voltage is taken across the capacitor, so that there is an improvement of the quality factor. That is, Q of the voltage will be the output from the capacitor. Though the antenna output is giving you a small voltage, it will be multiplied by the quality factor of the LC circuit. That's how the standard trick appears for most of the antenna outputs, and this transmission line is a replacement for such type of LC circuits. So to realize a system on a chip, that is an RF circuit along with the antenna and other things, is the common practice these days, particularly for IoT enabled devices. That is, if you want to connect your TV or air conditioner or rice cooker or geyser, etc. in your home devices to internet, we are now getting an IoT enabled device or a dongle type of thing. That is basically made as a system on a chip, or the RF electronics as well as the antenna and other things are prepared on the same board, and that board is going to have this sort of a transmission line structure only to get the effect of inductance, capacitance, series resonant or parallel resonant circuits. So these equations play a very important role in the design of those things, and we are also going to see some more applications in the coming classes of these things. Now let's go to the points where we stopped earlier. So this is for the case of an open circuited transmission line where the end of the line is just left open, and if the line length is less than lambda by 4, it acts like a capacitor. If the line length is greater than lambda by 4, it acts like an inductor, and if the line length is exactly lambda by 4, it acts like a series resonant circuit. If the line length is exactly lambda by 2, it acts like a parallel resonant circuit. That is, quarter wave line, if it's open circuited on one end, will act like a series resonant circuit. Similarly, a half wave line will act like a parallel resonant circuit. Because of the simplifications what we have got in the equations, we are able to come to this conclusion. So purely resistive loads are generally avoided. Purely reactive loads are connected for matching and tuning and other applications, where these type of transmission lines play a very important role. Open circuited lines are used along with the microstrip circuits, okay, whereas short circuited lines are only used with normal coaxial cable and strip line and other types of circuits. Okay, so the short circuited line, which is having a length less than lambda by 4, is going to act like an inductor. Exactly if it is lambda by 4, the role is reversed. It is going to act like a parallel resonant circuit, where open circuited line of lambda by 2 acts like a parallel resonant circuit. So for a shorter length of that, with lambda by 4 length itself, if you can make a short circuit, you can get the effect of the parallel resonant circuit by this. If the length is more than lambda by 4, then it acts like a capacitor, and if the length is exactly lambda by 2, a short circuited line acts like a series resonant circuit. Okay, and again after lambda by 2 the performance repeats. That's what is indicated here, that again after lambda by 2 you see that the reactance offered by a short circuited line is positive, indicating that it acts like a inductor. So less than lambda by 4 or greater than lambda by 2 the performance is same. Similarly, less than lambda by 2 or greater than lambda by 2, 3 lambda by 4, it is going to give you the same performance like a capacitor. So this is one thing what we have seen, whatever we have discussed so far. We're just going to have a simple quiz type of thing from one website, samfoundry.com, and we'll go through all those exercises first, and then we'll come back to the regular discussions on these things. So these are the questions which I have in mind, which is from the website samfoundry.com. Let us try to go through this. Which of the following parameters does not exist in the transmission line equation? The transmission line equation is basically voltage to current relationship. dV by dz is equal to something of I, and di by dz is equal to something of V. So there, whichever one is not going to appear, you just have a look, and these ones, the options given are Z0, ZL, and propagation constant. As you know, the transmission line equation consists of this propagation constant, load, and characteristic impedance only. Then you can see that this transmission line equation consists of only secondary parameters Z0 and gamma, which are derived from the primary parameters. The propagation constant, load impedance, and the characteristic impedance are related in the transmission line equation. So the one which is not going to appear here directly is the R. That is simple resistance of the wire, which we have R, L, G, and C. I was telling you quite often. So then we have an infinite transmission line. The characteristic impedance is given by 50 ohms. Okay, a line is having a very long length, and it is found to give a characteristic impedance of 50 ohms. So what is the input impedance? As you know, characteristic impedance is the input impedance of a very long length of line. So it should be again 50 ohms. That is, option is D. That's the definition for your characteristic impedance as per our earlier discussions. Okay, so the best transmission length, effective transmission of power, right, is how much? Effective transmission means there should not be any reflections. So it should be, yes please. Yama? Share cheyaleda? Are, sorry. Okay. Maybe. Yes. Transmission line equations, we are going to work out the problems. So let's start again the problem for those who missed it. The first question is, now is it okay? Right. Okay. So let's go back to the point where we have been discussing on these transmission line equation. So which of the following parameters does not exist in the transmission line equation? So R, Z0, ZL, and propagation constant. That is, these are the options we have, and the answer is that A. Why is it so? Because in the transmission line equation, we normally have the relationships of your Z0 and gamma, they are secondary constants, and is also related to the ZL. So R is a primary constant which doesn't appear directly in the transmission line equation. Okay, so answer is A. Then second question is, for an infinite transmission line, the characteristic impedance is given by 50 ohms. Find the input impedance. The definition of characteristic impedance is that is, infinite transmission line input impedance is 50 ohms. So whatever is the input impedance is asked, it should be same as your characteristic impedance. That's by the definition of characteristic impedance itself. That's why out of the options, D is the correct answer for these things. Okay, and next we have the best transmission length For effective transmission of power, when can we have very good power transmission happen? Okay, so it is L by lambda by 8. Maximum transmission of power will occur when the transmission line is matched. So this implies that input and characteristic impedances are same. This condition is possible for L is equal to lambda by 8 or L is equal to infinity. But L is equal to infinity is not possible. So the best option is L is equal to lambda by 8. Okay. So this is next one. And the length of the transmission line is same as that of the wavelength. Then which condition holds good? That means L is equal to lambda. What is that? Zin is equal to Z0. Is it correct? Or Z is equal to Z0. Or ZL is equal to Z0. Or Zin is equal to ZL. Okay. So you can see that Zin is equal to ZL because every half wavelength the performance repeats. So when the transmission line has a length same as that of the wavelength, the input impedance will be same as the load impedance. So even if it is half wavelength, you will get the same thing. Okay. So here the transmission line acts like a buffer or a D flip-flop. That means it will give rise to a delay of one time period. If it is having a length of lambda, for the signal to travel, it takes one time period of that. That means one pulse delay. If you are looking like a D flip-flop, this is the type of transmission line which we are going to have. Okay, but please remember, unless the wavelength is very, very small, that is, unless the frequency of operation is very, very high, we cannot think of these things, because if the length is 1 by lambda, there will be good amount of attenuation also, even if we use high quality transmission lines. Okay, so if the length is say 5 centimeters, 10 centimeters, or 50 centimeters lambda, then it may be okay. But if the length of the wire is coming out as hundreds of meters or even more at the operating frequency of 10 megahertz, 50 megahertz or something like this, then the line length is going to cause good amount of attenuation. So a D flip-flop at very, very high frequencies using this is a difficult proposition. So we ask for alternative methods to get the delay flip-flop operation. Okay. Similarly, we also need this sort of transmission lines for our radar operations, where the radar has to identify only a moving target. That means the previous return signal from the target and the present return signal from the target. We try to compare and see whether there is any difference between them. Then only we are going to give an indication. The same situation as you find when you are going into somebody's house where there is a dog kept for security purposes there. So you can see, if you move, then only the dog is going to bark or do something and other things. If you stand still, the dog is not going to do anything, because dog's eyes are also moving target indicators. So in a moving target indicator, that is, when there is movement, then only indication must be there. That means previous signal from the target and present signal from the target. We try to compare and see whether there is any difference. So the previous signal which we have received has to be kept in a D flip-flop type of transmission line structure so that it can be compared with the present input. So this is a very standard example for that. And if the line length is coming out to be very, very large for operating frequencies of hundreds of megahertz or tens of megahertz, etc., then we use alternative methods to realize the operation of the transmission line. Okay. Acoustic lines are used. Okay. So these are some of the additional points which you can keep in mind in this context. The input impedance of a half-wave transmission line with a load impedance of 12.5 ohms. 12.5 ohms is the load. Length of the line is half-wave transmission line. L is equal to lambda by 2. So what is going to happen? As we know, L is equal to lambda by 2. The performance is going to repeat. So the option is D, because the same impedance is going to be appearing at the input. Okay, I told you it is used as a buffer or an extension of a transmission line, so that there is no disturbance to the voltage and current and other things for the source due to the increase in the length. So if you have any inaccessible points to connect a load, we extend the transmission line by about lambda by 2 and connect the load so that there is no disturbance to the voltage and current waveforms on the rest of the transmission lines. So the condition for the quarter wave transformer is, this. That is the characteristic impedance, input impedance, what you are looking for, and what is the load impedance. If you see, they all should follow like a geometric mean type of equation. So here you can see what are the options. So the characteristic impedance must be geometric mean of the load impedance and the source impedance what we are looking for, or the input impedance what it has to come. The load impedance has to get transferred as a different value at the input by the presence of this quarter wave line. So the quarter wave line characteristic impedance must be geometric mean of the input impedance and the load impedance. Next, 7th question. Find the characteristic impedance of a quarter wave line with input and load impedances given by 50 and 25 respectively. So input impedance is 50 ohms what we want, and the load impedance is only 25. That means a 25 ohm load should appear as a 50 ohm load to the source. So in between this, what can be connected? So that is a quarter wave line, and its characteristic impedance must be square root of 15 to 25. So it is 35, okay, 0.35 ohms. So if you can connect a lambda by 4 line with characteristic impedance of 35.35 ohms, then a 25 ohm load can be connected as a double of it, 50 ohm load. Okay, suppose we reverse it. Yeah, it works on the same lines. That is, to connect a 50 ohm load, it appears like a 25 ohm load source impedance also. Okay, so it can be used either ways. Please remember, it's not that it converts only 25 ohms to 50 ohms. It can convert a 50 ohm to a 25 ohm case also, because a transmission line is basically a symmetric one, a symmetric circuit or a network. Next question is 8. Find the load impedance in a quarter wave transformer with characteristic impedance of 75 and input impedance of 200 ohms. So characteristic impedance is given, input impedance is given, and now we are asked to find the load impedance value. That means how much load is required to connect with a 75 ohm quarter wave line and see that the input impedance comes out as 200 ohms. So 200 into ZL must be the Z0 square, that is 75 square. So ZL, the load impedance must be 75 square by 200. So whatever value it comes, we should be able to take it. Okay, so you see here 75 square by 200 is appearing as 28.125 ohms. So the option is A. Okay, so a 200 ohm is what you are looking for, and 75 ohm line we have, and if you want a load to match with all these situations, then it has to have a value of 28.125 ohms. Okay, so next question, we will just wait for a while. Okay. After today's discussion, maybe we can do it. So 10th question is that the purpose of the transmission line equation is to find primary parameters, secondary parameters, find the reflection coefficient, impedance matching. Okay, so it is to find the impedance matching. The transmission line is useful in finding the length of the line, which gives maximum power transfer. So it is maximum power transfer. In this context, we simply say it as impedance matching, and thereby it goes very comfortably with this. Okay, so these are some of the basic questions what we have, and if you want some more questions, you can always work out. And which type of transmission line is called a one-to-one transformer? It's one of the standard interview questions. Please remember, one-to-one transformer means 1:1. That is, the transformer turns ratio is 1. So what is going to happen if the transformer has equal turns on both sides? So same impedance, whatever load time at the secondary side you are connecting, it appears on the primary side also. So, same impedance, if it has to be repeated, what should be the case out of the options given? L equal to lambda, lambda by 2, lambda by 4, lambda by 8. Okay, so the half wave transformer, it repeats. Okay, so the same things here. So Zin is equal to ZL. So it is considered as a 1-to-1 transformer. Okay, so it extends the impedance line. That's the only thing what we can discuss in these aspects. Okay, so there are many more questions to get familiarized with the type of questions what you are going to get in most of the interviews. These are very standard questions in the interview process if you want to appear for any communication oriented core jobs. Now, let's come back to the point where we stopped and continue our discussions on these things. Okay, so we discussed about these aspects, and this is one of very good graphical representation of the types of transmission lines. Please see, these are short circuited transmission line of length lambda by 4. So it acts like a parallel resonant circuit. Okay, and the second one is an open circuited transmission line of length lambda by 4. So thereby it acts like a series resonant circuit. Okay. Then third one is less than lambda by 4 short circuited transmission line. From our earlier graph, as you can see, it acts like an inductor. The fourth one is an open circuited transmission line length less than lambda by 4, so it acts like a capacitor. Okay, and then fifth one is lambda by 4 is this mark. So compared to that, we are having the length greater than lambda by 4. So a short circuited transmission line with length greater than lambda by 4, so it acts like a capacitor. Then the last one is a transmission line whose length is greater than lambda by 4 and it is kept open circuited. So open circuited line with length greater than lambda by 4, it acts like an inductor. So you can get the realization of an inductor with a open circuited line length greater than lambda by 4 or a short circuited line with length less than lambda by 4. Similarly, you can get the effect of a capacitor with an open circuited line less than lambda by 4 or short circuited line greater than lambda by 4. Okay, so these are some of the options what we have, and thereby you can see whichever way it is convenient at any specific location, and whether an open circuited line can be used or not. Accordingly, we choose either we should go for open circuited, short circuited, greater than lambda by 4, less than lambda by 4. All these things are worked out. Please remember, these lines work like an inductor or a capacitor over certain length only. It means from lambda by 4, if you reduce the length by small amount and other things, yes, and the frequency should correspond to this. By changing the frequency, the same thing may work up at another frequency as an inverted element. So please be careful that once you have designed it, you can't scale it up beyond a particular value. Then, now let's go to the next, another important way of looking at these transmission lines. As we see the transmission line equation, we are getting the voltage expression and current expressions in terms of two terms. One is a forward traveling wave, V0 plus e power minus gamma z, and the other one is a reverse traveling wave. That means this first term represents a voltage wave traveling from source to the load, whereas this represents a wave that is traveling from the load towards the source. Reverse traveling or return wave or return signal, all these are some of the names we use. This is the one which is very specific to the transmission lines, because all the power what we are giving to the load might not have been completely absorbed. Some part of the power will be returned or reflected from the load and it starts traveling towards the source. So that's the one which is accounted by this. That means if you see a general transmission line, once you excite the transmission line with some signal, within a very, very short duration, it comes to this sort of a steady state situation where There will be a forward traveling current voltage wave and a return traveling voltage wave. So these two things will form a standing wave. So a standing wave is what you can observe on the transmission line. The standing wave corresponds to the voltage. A similar standing wave corresponds to the current also exists because voltage and current are directly related through your impedance. Now, the same voltage equation we are now trying to write in terms of load current. Okay, so IL ZL plus Z naught into e power gamma Z prime plus ZL minus Z naught times e power minus gamma Z prime. Z prime is from the load as we start taking the calculations. L minus Z is taken as Z prime, and the load is expected to be at a distance of L from the source. That's what is our understanding of all these things. So now, if you see, what is the ratio of the return wave in terms of the forward wave? That means how much part of the incident power is reflected, is not utilized by the load, is kept back on the transmission line, which is going to be troublesome for us. So how much is the troublesome component with reference to the input component we are going to take, and here we have a new parameter of interest in these things, that is this ZL minus Z naught by ZL plus Z naught, ZL minus Z naught by ZL plus Z naught, that is load impedance minus characteristic impedance of the line by load impedance plus characteristic impedance of the line. If you take that parameter, that quantity is known as reflection coefficient, capital gamma. This is a Greek letter which is the first case in the gamma. As gamma you might have seen it normally in a different way, which is basically a fourth case letter. This capital gamma is the first case gamma. So this gamma is the way we try to represent the reflection that is going to happen right at the load location because of the difference of the load value with the characteristic impedance of the line. If ZL minus Z naught is going to be finite, if there is any difference between ZL and Z naught values in terms of real and imaginary components, then there is going to be some unwanted return signal which is having some relation with the input signal through capital gamma. So capital gamma is the way we try to look at it, how much unwanted thing is happening on a transmission line. So that is given as capital gamma is defined as V0 minus by V0 plus. V0 minus is at the load location, whatever is the reflected voltage wave amplitude, and V0 plus is at the load location, whatever is the voltage wave amplitude we are going to take, and phase also. V0 is AC quantity, okay, is a minus or plus. So we take both amplitude and phase part of these voltages, and this is also given as ZL minus Z naught by ZL plus Z naught. As we know, ZL can be complex, and normally Z naught is real, but in the worst case it can also be complex. So finally, in general, we take this capital gamma as a complex quantity with mod gamma as the magnitude part of it, and theta small gamma is the phase of the reflection coefficient. Okay, so basically we should remember this capital gamma is a complex quantity. Capital gamma is equal to ZL minus Z naught by ZL plus Z naught only at the load location. As you travel along the transmission line at various locations, it is going to have some additional things coming up. So in terms of this capital gamma, whatever we have just now defined, the voltage and current expressions are shown. So the voltage expression and current expressions are given in terms of the load coordinates, Z prime. So IL by 2 ZL plus Z naught e power gamma Z prime times 1 plus capital gamma e power minus 2 gamma Z prime. Okay, so this is the way we voltage wave is going to be represented in terms of capital gamma. Similarly, the current expression can also be worked out, and it comes out as IL by 2 Z naught, Z alpha Z naught times e power gamma Z prime times 1 minus e power 2 gamma Z prime. So, gamma is the voltage reflection coefficient, because we are taking V naught minus by V naught plus. So, this is, this is the way we are taking up the definition. So, hence, for the current, you are going to get a negative sign there, because the two currents will be opposing each other. They are traveling in two reverse directions. Okay, and this same thing can be given in terms of cos function and sine functions also, instead of exponentials. So, in terms of cos and sine functions, what is happening is expressed in this. Okay, and please remember, we are taking that the gamma is simply equal to j beta. Okay, that's why beta is directly appearing, though in the first two equations the gamma is appearing. Small gamma represents propagation constant, capital gamma represents reflection coefficient. That's how the notations go in this subject. Small gamma is our propagation constant, which is expressed in per meter, whereas capital gamma is our reflection coefficient, which is a dimensionless quantity, because it is ratio of the voltages. Okay, so in terms of the cos and sine functions, the current on the transmission line can be represented in this manner: IL cos beta Z prime plus J VL by R naught sin beta Z prime. Okay, so please remember, this gamma, capital gamma, reflection coefficient, whatever we have been talking of, is a complex quantity, and its magnitude and phase will be changing along the transmission line in a general case, because on a transmission line the voltage will have different amplitudes and phases at different locations. So, forward wave will have different voltages and phases. Similarly, reverse wave also will have different voltages and phases in a general case. So, the ratio is going to get changed. So, this ratio is also difficult to measure. In good olden times, there was no way to measure this particular quantity, because the voltage and current on a transmission line is finally a standing wave, a mix of these two things. So, dividing the forward wave and reverse wave and taking the amplitudes of the forward wave and reverse wave to get the ratio of them was a difficult thing in good olden days. So, there was no way to measure this, and even if you can measure, the most important point in measurements is you should be able to measure a number of times, so that your observations can be taken as an average, and finally that reduces the measurement error. That's what we do. With capital gamma, that is a reflection coefficient, there is no repetition of the values that is possible, because at every location the gamma value is going to change. So, even if you can measure, there is no way that you can get the repeated values of the same thing. So, your measurement error is likely to be more in your measurement, and the measurement itself is a difficult process. So, to overcome these problems, people have come out with a different parameter, which is very simple, again dimensionless and measurable, and it is measurable at a number of locations, so that you can take an average of these values and reduce the measurement error. That's how a standing wave ratio has been introduced. The purpose is to see that we can measure this quantity at number of locations simultaneously without much of a problem, and see that we can take an average value of this and see that the measurement error is very, very minimal. Okay, this is what we know in all our measurements classes. Precision is very, very crucial for all your parameters of interest. So, repeatability we should identify. In such a way, we have to introduce the parameters. So, the standing wave ratio is introduced, which is basically defined only for standing waves. Standing wave means a forward wave plus a return wave together. So, once you have a forward wave and a return wave, which are having different amplitudes and phases. But at certain locations, the phases of these two things will add up. At certain other locations, the phases of the forward and reverse voltage wave will be opposite to each other. So when they are opposite, you get the minimum value of the summation. When they are in phase, you will get the maximum value of the summation of these two waves. So the standing wave will have certain maximum values at certain locations, minimum values at certain other locations. So the standing wave ratio means what is the ratio of this maximum value, what you are getting on the wave at different locations. What is the minimum value what you are getting? If you take the ratio, that is known as standing wave ratio. Okay, maximum to minimum voltage ratio along a finite terminated line. Because unless you terminate the line, you can't have any wave that is traveling along the length. If the line is terminated with impedance which is other than characteristic impedance, then only you will have forward wave and return wave are together a standing wave. And in a standing wave only you can think of measuring maximum voltage and minimum voltage. And these maximum and minimum values will be repeating if the line is lossless. Why it should be lossless? Because at maximum locations, the same value of forward wave and reflected wave, if you can add up, then only you will get the same maximum value. Similarly, at minimum locations, unless you have the subtraction of the same forward wave and return voltage wave amplitudes, you can't have same minimum value. So if you want to get same maximum and same minimum, the requirement is that the line must be lossless. Luckily, we have many of the transmission lines used at very, very high frequencies, VHF and UHF and further. The lines can be considered almost like a lossless line. So at all these high frequencies, we can easily imagine that they are lossless lines, and thereby the S value can be measured at various locations by taking the ratio of maxima and minima at several locations. That's the advantage with your S value. Standing wave ratio is represented as S, and it is a dimensionless quantity, and it is only a real number. Why is it a real number? Because it is simply the ratio of two magnitudes. Magnitude part of the voltage wave when there is a maximum combination of reflected and incident waves. Similarly, minimum also is going to be there wherever the phases are going to oppose each other, thereby Vmax to Vmin. They are simply numbers, and the ratio is again going to be a simple real number. So Vmax comes with V reflected and V incident summed up exactly in phase, and V min will come up when V incident and V reflected get subtracted. So Vmax is V incident plus V reflected, and V min is V incident minus V reflected. So if you take V incident, voltage incident onto the wave or input wave, if you take out from numerator and denominator, you are going to get it as 1 plus mod gamma by 1 minus mod gamma. This is the relationship between the gamma and VSWR. Okay, and if you want the other way, that is what is gamma in terms of VSWR, the second equation is going to help us. So by doing component on dividendo, you can see that mod gamma is given as S minus 1 by S plus 1. So gamma and S relationship is indicated. Please remember, whenever we are talking of S, it is the magnitude of the reflection coefficient that only matters. The phase of the reflection coefficient has no direct relationship with VSWR and other calculations. Okay, so this mod gamma, as we see, is reflected to incident voltage ratio amplitudes wise. So it can have a minimum value of 0, because when there is no reflection, you can get mod gamma as 0, and when there is complete reflection, that means the wave is not able to proceed into the load and completely gets reflected, you will have the reflected value same as incident one, either in phase or opposite phase. If it is in phase, the gamma will have a maximum value of +1, and if it is out of phase, the gamma will have minimum value of -1. So in general, the reflection coefficient has values between -1 to +1. Mod gamma, that is magnitude part of this gamma, is going to be definitely between 0 and 1. It is a closed boundary. Please remember, the reflection coefficient magnitude changes between 0 and 1. If that is the case, what is the range of values possible for this VSWR, voltage standing wave ratio, the worst? So as you substitute 0 in your expression, 1 plus mod gamma by 1 minus mod gamma, you get the S value as 1. If you substitute this mod gamma as 1, then you are going to get S as infinity. So the VSWR, the voltage standing wave ratio, is going to have a range of values possible as 1 to infinity. Okay, minimum value is 1, maximum value is infinity. Please remember, S is a dimensionless quantity. So with one number, you can indicate whether the line is behaving well or in a not so well or very, very bad situation. If the line impedance is very much away from the load impedance value, then the VSWR value is going to be very, very high, like 2.5, 3.6, or 10, 8, or some numbers like that, indicating that the line is thoroughly mismatched. If the VSWR on a line is found to be 1, when can we have the value of 1? When mod gamma is equal to 0. When mod gamma equal to 0 means that the ZL and Z0 are same. That is, the load impedance and the characteristic impedance values are same. So when the line is completely matched, what we call the condition ZL equal to Z0 as a matched condition. So that is giving you the S value as 1. That is, S, if it is 1, we are very happy situation, that is matched condition. All the power from the source will thoroughly get transferred onto the load without any reflections. If the value of S is other than 1, anything higher than 1, then it indicates a mismatch condition. And more it is away from 1, more and more reflections are likely to happen on the transmission line accordingly. So S clearly indicates the quality of the transmission that is happening on a particular transmission line from the source to the load. Okay, so there is a meter also available, which is known as standing wave ratio meter, which can be used to directly measure this, and thereby you can definitely get a direct indication how good the line is working with the measurement of this VSWR. If it is 1, very happy, very comfortable, very comfortable. If it is away from 1, yes, the things are getting worsened as you, right? That's what the clear indication. Now, what happens for the precision aspect of this? As you can see on a length of a transmission line, the standing wave is going to have several maxima and several minima. And you know very well, if there is any standing wave, the maxima will be spaced at about lambda by 2 distance. That means 2 successive maxima, if you can identify and try to find out what is the distance between them on the transmission line, it's going to be equal to half wavelength. Similarly, 2 successive minima or 2 adjacent minima, if you identify and find out the distance between them, it is also again lambda by 2. So here you will have several maxima on the transmission line, and as we consider lossless lines only, the maxima values should be same. Similarly, the minima values also must be same. So if you can take the sensor on a transmission line to various locations, you will see that the sensor output connected to a meter is going to indicate the maximum and minimum values. And if you take the maximum values appearing at various locations, and similarly the minimum values appearing at various locations. If you note down and take the ratios appropriately, then you will have several VSWR values available for you, and taking an average will give you a very precise value of S, or a very accurate value of S, and this is how the precision or the repeatability is established. So that's the importance of VSWR, and this is a measurable quantity, whereas capital gamma, the reflection coefficient, is not directly measurable, so simple as this. Of course, nowadays we have some instruments where the gamma value can be measured by splitting the forward waves and return waves on a transmission line. So for splitting purposes, we have power splitters available, and we try to send the power in specific directions and split the power, and see that one output of the splitter is going to give you forward wave, another output of the splitter is going to give you the return wave, and giving those two things to different instruments and measuring the values, we can find out the ratio, or directly giving the two outputs to a ratio meter, we can find the ratio of reflected voltage to incident voltage and find out the capital gamma, that is the reflection coefficient. That is what exactly is being done in your network analyzers, which are existing in various labs, though they are a bit expensive. Whereas VSWR, if you consider, it is very easy to measure, as well as the instrument used for this is quite cheap. So people try to depend on VSWR in the first place, and once it is the basic conditions are satisfied and the system is established well, in the final stage only people think of doing the measurements on this network analyzer and get satisfied with the reflection coefficient values to be within the specified limits. So this is how the VSWR is going to help us to give a first indication how good the system is working without any reflections. So that's the importance attached for your piece. So whatever we have discussed, let us recapitulate. Here, gamma, capital gamma is equal to 0, means there are no reflections, and it should give you the capital S value as 1. So this happens only when the load impedance is equal to characteristic impedance of the line, or when the load is matched to the transmission line, or we say the transmission line is match loaded or matched loaded. Like this, we have different ways of expressing the same condition. Second one is gamma is equal to -1, that is when the line is terminated with a short circuit, then the gamma is going to be -1, or the ZL is going to be 0, and when you substitute gamma equal to -1 in your expression for S, you are going to get it as infinity. That means for a short circuited line, the transmission line at any location, you can see that the VSWR value is going to be infinite. Similarly, if gamma is equal to +1, then also you get S is equal to infinity. When do we get gamma equal to +1? When the load impedance value is infinity, or when the load is open circuited, you will get capital S as infinity. Now coming back to the same situation from the VSWR point of view, that is, if somebody has measured that the VSWR is equal to infinity, can we conclude something about it? Yes, we can conclude only that the line can be short circuited or open circuited, but we cannot exactly pinpoint whether it is short circuited or open circuited. Either of the conditions will give you same capital S value. VSWR infinity is ambiguous point, whereas VSWR is equal to 1, suppose we are able to measure. It clearly indicates only one condition that is possible, that is, it is a condition for matched termination or matched loaded. So ZL is equal to Z0, and it also indicates clearly that the reflection coefficient is 0. Whereas infinity can indicate reflection coefficient of -1 or +1. Why does it come like that? Why is the ambiguity? It is because the VSWR is dependent on mod gamma. It's not on actual gamma value, it is dependent on mod gamma. So mod gamma for -1 or +1 condition is same. Thereby, it gives you the same VSWR value, or the ambiguity is between short circuit and open circuit. Okay. And as you know, the ratios in communication engineering are normally expressed in terms of dB scale. If you want to convert this VSWR into dB scale, what we try to do is we take the 20 log of S. Okay, why 20 log is required? Because we are taking the voltages ratio. Okay, maximum voltage to minimum voltage of a standing wave is what we are considering for VSWR. So it is 20 log capital S that has to be taken into account. Okay, so this is how we try to identify the VSWR, capital gamma, and other things on the transmission line to represent its condition with reference to matching. Whether the line is having any reflections or all the input power is going into the load or not, we can estimate with these values of capital S. Okay, so this is a very important parameter, and in most of the institutes or colleges, this S value measurement is going to be an experiment in your final year class. Okay, VSWR of a given load, or by measuring the VSWR and something else, you are going to determine what is the load that is given, what is the ZL value of the load that is given, you are going to estimate. Okay, and the VSWR meters are going to be present in all these labs, which are just around 10,000 rupees or so. Compared to network analyzer, would cost you around lakhs of rupees. So that's the significance of introducing this capital S or the VSWR. Okay, so far this is all done. But in future, please remember, this is only for future cases where we are going to use magnetic materials, magnetic conductors, magnetic things in our signal transmissions. That's at very, very high frequencies, beyond 30 gigahertz. We are going to use this sort of things in future. So there, we are going to talk about the current on a transmission line. The reflection coefficient is also going to be defined in terms of I reflected to I incident, and the voltage reflection coefficient and current reflection coefficient will have a negative sign. Okay, and thereby you will have some changes that are to be taken care in the reflection coefficient. However, the VSWR is going to be same, whether you are considering voltages ratio or the current ratio. As you can see here, it is going to be same value. That's why people don't specifically mention it is voltage standing wave ratio and something else as current standing wave ratio. Simply they say as standing wave ratio. It means either of them. Only for the reflection coefficient, you will have changes of the signs, whether it is voltage reflection coefficient or current reflection coefficient. Okay, so let's not get confused with all that. In the present, we have only voltage reflection coefficient, voltage waves, and voltage things because we are using still electrical conductors like brass, aluminum, copper, etc. Okay, so unless otherwise specified, let us not get confused whether it is voltage reflection coefficient or current reflection coefficient. We talk of only voltage reflection coefficients, which will have +1 for open circuited case and -1 for short circuited case. Okay, so and standing wave ratio will have a range of values possible as 1 to infinity for any case. 1 is the most favorable situation. Infinity is the worst possible condition as far as the transmission of the power is concerned. Okay, so this is something on the reflection coefficient, standing wave ratio, what is the importance, where do we use, what is the significance of these aspects. Okay, so these are the most important things, and in many of the competitive exams, you will get some questions on these things only, like if the gamma is equal to -1 for a particular type of transmission line, can you estimate what is the type of termination that is likely to be there? If gamma is equal to 0, what is the VSWR value you are going to get? Like this, there can be questions in the competitive exams. So please get ready or please follow some books available in the market regarding these bit questions or interview type of questions. But please remember, in most of the cases, the interviewing person is likely to commit a mistake of asking what is the range of values of gamma. Okay, so please be careful. Capital gamma, that is reflection coefficient in complex form, is going to have a range of values of -1 to +1. If it is the magnitude of the reflection coefficient is only going to vary between 0 and 1. But most of the times people get confused and they expect the answer only 0 to 1. So please tell them that the gamma is going to have -1 to 1 in complex form. If it is only magnitude you are looking for, then it is 0 and 1. Please try to elaborate an answer. Then definitely you will not get into any trouble. Otherwise, most of the unfortunate situations are that people expect the answer for gamma as 0 to 1, which is not correct. The range of values of gamma is -1 to 1 because it is amplitude and phase both are included. Whereas magnitude only changes between 0 and 1. Okay, so please be careful when you are answering this type of questions, particularly in electromagnetic waves and transmission line subjects. People give you some confusing questions or ambiguous questions only in general. So let's be careful about it. Right. So one more thing what we need to understand at this point of time is that, as you can see, that the standing wave is going to have some final value at the location of the load by looking whether the standing wave is between minimum to maximum at the load or after the maximum to minimum at the load. You can estimate what is the type of the load. So that is another interesting feature of this type of transmission lines. Okay, and the voltage minimum, if it has to occur, then we know that the phase of the reflected and incident voltage waves must differ by pi radians. So the reflection coefficient from the load as you move on a transmission line of not having any attenuation, then it is going to vary in terms of beta, and if theta capital gamma is the reflection coefficient and at a distance of z prime, if the load voltage minimum is going to occur, then by moving the reflection coefficient from the load up to this point of minimum, you will be adding a phase of 2 beta z prime. So 2 beta z prime minus theta gamma must be equal to the voltage minimum location phase, which is e power minus j pi. So e power minus j pi is -1. Thereby the theta gamma, that is the reflection coefficient phase value at the load, can be estimated by knowing the distance to the first minimum from the load and finding out the beta value from the given signal parameters, like the frequency of the signal. Okay, so 2 beta z prime is the distance what you are moving from the load. So the theta gamma, that is the phase of the reflection coefficient, is going to vary by theta gamma minus 2 beta z, and it must be equal to -pi. Why it should be equal to -pi at the location of the voltage minimum? Because voltage minimum occurs only when the reflection voltage and the incident voltage are opposite in phase. So the ratio must be equal to -pi. So theta gamma minus 2 beta z prime is equal to -pi, or theta gamma is equal to 2 beta zm minus pi. That zm indicates what is the distance to the first minimum. So by measuring this distance of zm prime and knowing the beta, then you can estimate what is the theta gamma. This is one of the experiments what you will be doing in your lab if an unknown load is given. What happens is, if an unknown load is given, we connect that load at the end of the transmission line, take the capital S value from the meter connected to this, that is VSWR is measured. So that gives you what is the mark of the reflection coefficient. And by knowing the distance from the load to the first minimum, that is Zm prime, you can get the reflection phase value theta capital gamma. So mod gamma is known from S, theta gamma is known from Zm prime. Then taking these two things, you can use the basic equation for the load to reflection coefficient relationship. So that is ZL by R naught is equal to 1 plus gamma by 1 minus gamma, where mod gamma is already measured through VSWR, theta gamma is measured through Zn prime. So once these two things are known, ZL by R naught can be calculated from 1 plus gamma by 1 minus gamma. Gamma is a complex quantity. Then once we know the R naught of the given transmission line, we can find out the ZL value. That's how we are going to do an experiment in the lab to get the impedance value of the given load. That is, what is the value of real part, that is RL, and what is the value of the imaginary part or the reactance at the given frequency of operation. We are going to get these. Okay, so the voltage minimum. Why do we choose? We get the same things from the voltage maximum. Corresponding equations can be developed for the voltage maximum also, right? But we try to choose only voltage minimum because it is sharper. That is, as you move on the transmission line to find out where the voltage minimum is, across this, the slope of the characteristic is very, very high. What is the variation in the electric field or the voltage wave across this location for various distances? If you see, the voltage changes are quite small. So the slope is very high. You can precisely find out where the voltage minimum is. Whereas when it comes to voltage maximum, the change in the voltage value at various locations surrounding the maximum is very, very less. The slope of the characteristic is less, so you will not be able to precisely find the distance from this. So we avoid taking the measurements with reference to voltage maximum, and we try to stick on to voltage minimum for our measurements. Of course, for VSWR measurement, we need to find this, and we are not looking at the location, we are looking at the maximum value of this voltage wave. So whether it happens here or here, it doesn't matter. That's how the repetition of the values is going to give you less error in this. That's why VSWR is always chosen for the measurement part. Okay, so VSWR is more useful and more comfortable. It's simply a number, but it really reflects the quality of the power transfer in a particular transmission system from the load to the load, from the source to the load is given. Okay, so that's the importance associated with these things. Okay, now let's go back to some of the problems associated with this in the subject and try to understand these aspects to get more familiarity with these things. Okay, so let us try to choose problems from reflection coefficient and other aspects of this transmission coefficients. Okay, so the reflection coefficient of a wave with a transmission coefficient 0.35 is, that means we are trying to get what is transmitted into the load, and we would like to find what is not transmitted. So whatever is transmitted is given only 0.35. So rest of it must have been reflected, because there is no other way the power loss is going to happen. So coefficient means what is the transmission that's going on by what is the incident. Similarly, reflection coefficient means what is the reflection that is happening by what is the incident power, what is their input power given. So transmission coefficient is transmitted voltage by incident voltage, whereas reflection coefficient means reflected voltage by incident voltage. So out of the total power, it is the transmission plus reflection that can happen. So incident power is equal to transmitted voltage plus reflected voltage. So when you take these two things with reference to incident voltage, one is equal to transmission coefficient plus reflection coefficient. So transmission coefficient is given as 0.35, so reflection coefficient must be equal to 0.61, so that the total sum is equal to 1. Okay. Now the second question is, incident wave amplitude is 24 units. Find the reflected wave amplitude if the reflection coefficient is 0.6. 0.6 is equal to something by 24. Okay, so 24 is there with us, 0.6 is there with us. So multiplication of these two things will give us the reflected wave amplitude. So 24 into 0.6 is 14.4. So the option is A. Okay, so reflected wave amplitude is asked, incident wave amplitude is given, and reflection coefficient is also mentioned. So reflection coefficient is equal to reflected wave amplitude by incident wave amplitude in terms of magnitude of all the things. So 0.6 is equal to something by 24. What is that something? X is equal to 0.6 is 24. That's all. You can find out these things. Number 3 question. Find the reflection coefficient of the wave passing through two media having intrinsic impedances of 4 and 9. So this is what we have done earlier. Reflection coefficient, that means when the wave is trying to enter from one medium to another medium, we know eta 2 and eta 1 are the two intrinsic impedances. So when there is a difference between them, the wave is going to be reflected, and how much is that? It is also going to follow the same rules as we have discussed in this case. So again, on the same lines, eta 2 minus eta 1 by eta 2 plus eta 1, you can use to get this. See. So eta 2 minus eta 1 by eta 2 plus eta 1. That is ZL minus Z0 by ZL plus Z0 type of things, whatever we have worked out earlier. So you can see 4 and 9. So it is 9 minus 4 by 9 plus 4. Why 9 minus 4? Why not 4 minus 9? Okay. So we are taking that the medium where the already wave is traveling has an intrinsic impedance of 4, and the medium into which the wave is going to enter, he is going to have an intrinsic impedance of 9. That's what is the understanding what we get from this. So the medium which is having an intrinsic impedance of 9 is appearing like a load, whereas the medium which has the intrinsic impedance of 4 is already having the wave traveling through it. So it appears like a transmission line of characteristic impedance 4. So 9 is the load impedance, 4 is the characteristic impedance of the line. That's what is the understanding we have. So the reflection coefficient is ZL minus Z0. So 9 minus 4 by ZL plus Z0. 9 plus 4. So 5 by 13 is 0.38. That's all. The reflection coefficient can be calculated for this case. Okay. Then the reflection coefficient of a wave traveling through two media having permittivities of 4 and 9 on the same lines. Permittivities are given. So we need to find what is the intrinsic impedance from these calculations. So finding out the impedance, intrinsic impedances, and then finding out in the same manner will give you the reflection coefficient of 0.2. Okay. So permittivities and the intrinsic impedance, how are they connected? Intrinsic impedance is equal to root mu by epsilon. So eta 2 minus eta 1 is root mu2 by epsilon 2 minus root mu1 by epsilon 1. We consider that these mu2 and mu1 values are same. So similarly in the denominator also we are going to do. So this is going to give you root epsilon 2 minus root epsilon 1 by root epsilon 2 plus root epsilon 1. That is how the reflection coefficient is going to be. When the values given are 4 and 9, so epsilon r1 is 4, epsilon r2 is 9, so square root of 9 minus square root of 4 by square root of 9 plus square root of 4. So 3 minus 2 by 3 plus 2, 1 by 5, that is equal to 0.2. We are going to have for this. Okay, so this is the question number 4, where we have the earlier concepts coming into this. Now, calculate the transmission coefficient when the incident and transmitted amplitudes are 10 and 7. Incident voltage wave has amplitude of 10, whereas the transmitted voltage wave has an impedance of 7, has a value of 7. So it is 7 by 10. It should be 0.7 because transmission coefficient is defined as the transmitted voltage amplitude by incident voltage amplitude. So 7 is the transmitted one in this case and 10 is the incident one. So 7 by 10 is going to give you 0.7. Right? So again, the next question is on the same lines, transmission coefficients. Question number 8, let us try to discuss now for more familiarity. Reflection coefficient of a transmission line having characteristic and load impedances of 50 and 30 ohms. So reflection coefficient is going to be calculated at the load location. So characteristic impedance is given as 50, whereas the load impedance is given as 30. So 30 minus 50 by 30 plus 50. Okay. So characteristic impedance is 50. That ZL minus Z0 by ZL plus Z0. So ZL is 30. Yeah, there is a small mistake here. It is minus. It has to. Okay. So 50 minus 30 it is 4. 30 minus 50 is the case. So reflection coefficient is going to be minus 1 by 4. Okay. So this is 1. The next question number 9 is matched line, the transmission coefficient is completely 1. Because reflection coefficient is going to be 0, it is complete transmission into the second one. So it is maximum power is transferred from transmitter to the receiver, and so there is no reflection coefficient, hence the transmission coefficient must be unity. Number 10, find the power reflected in a transmission line. And the reflection coefficient and input power are 0.45 and 18 volts. Input power is 18. Input voltage must be 18 volts and the reflection coefficient must be 0.45. So 0.45 is equal to x by 18. So x is equal to same. Okay. So x is equal to, in terms of power we are talking about directly. So it is 18 watts. So it is square of these things what we are going to have, and the reflection power we are going to calculate from this. So that is 3.645 watts it should be. Okay. Now number 12. The reflection coefficient of a short-circuited transmission line is -1. Is it true or false? Obviously, it is true. Okay. For short-circuited transmission line, it is maximum reflection, and that too reflection is going to happen because the current must be maximum there and voltage must be 0 at the location of the short circuit. So the voltage got to be 0, the reflected and incident ones must be opposite in phase in terms of voltage when we are talking about. So reflected voltage is equal to minus V incident. So the reflection coefficient is V reflected by V incident, that is equal to minus V incident by V incident, or it should be equal to -1. So thereby it should be true, that is A. So that's how you can find out some of the interesting questions for these transmission lines, and this is about the transmission line reflection coefficient and other aspects. Okay. So then we will see some questions in the standing wave ratio and other calculations. So here we are going to talk on standing wave ratio, SWR. So why does the standing wave ratio occur of some value? It is due to impedance mismatch, okay, or reflections, or poor transmissions you can say. So impedance mismatch results in standing waves along the transmission line. Okay, and it shows the variation of the wave amplitudes due to mismatching. Okay, and standing wave ratio is defined as ratio of voltage maximum to voltage minimum, or ratio of current maximum to current minimum, or product of voltage maximum to voltage minimum, or product of current maximum and current minimum. Okay, voltage standing wave ratio or current standing wave ratio are on the same lines. So SWR is defined as a ratio of amplitude maximum to amplitude minimum. So voltage max to voltage min is the case. So given the reflection coefficient is 0.6, what is the standing wave ratio? What is the relationship between them? That is 1 plus mod gamma by 1 minus mod gamma. That is 0.6 is equal to 0.6, 1 plus 0.6 by 1 minus 0.6. That is 1.6 by 0.4, so that must be 4. So that's how you will have the reflection coefficient as 4 in this 1 plus 0.6 by 1 minus 0.6 or 1.6 by 0.4, that is equal to 4 of this. So, and another case, the maximum and minimum of a standing wave are given 6 and 2. So find out the voltage, that is 6 by 2. So it must be 3. Okay. And find the standing wave ratio if the load impedance is 250 ohms connected to a transmission line of 75 ohms. So how do we do it? We do it by first finding out capital gamma and then putting it into this case of this. But when you have resistive loads, you can make a simplification. So capital gamma is simply ZL minus Z0 by ZL plus Z0 magnitude part of it. ZL is resistive, that is given as 250 ohms, and Z0 is also resistive. So RL minus R0 by RL plus R0. So this is what the deflection coefficient is going to be. Then if this is the case, what is S? S is equal to 1 plus gamma by 1 minus gamma for resistive loads. So 1 plus RL minus R0 by RL plus R0 divided by 1 minus RL minus R0 by RL plus R0. So when you make the simplification, you will get it as simply RL by R0 if RL is greater than R0, which is the case. Otherwise, you should write it as R0 by RL. RL by R0 or R0 by RL, whichever is greater than 1. That is how the S value is going to be defined. So 250 ohms by 75 is the direct answer what you can have in this. So 250 by 75, that is equal to 3.33. You can give the answer very, very fast if the load impedance is resistive. It is simply RL by R0 or R0 by RL, whichever is greater than 1. Please remember that S is always greater than 1 and it can range up to infinity. Thereby, you should see which ratio is appropriate depending on the load impedance and the characteristic impedance of the system. Okay, now find the reflection coefficient of the wave with VSWR equal to 3.5. So if S is given, how do we find the gamma? It is exactly mod gamma what we can find, which is given as S minus 1 by S plus 1. So 3.5 is given, so S minus 1 by S plus 1 is 2.5 by 4.5. So 2.5 by 4.5 is going to give you 0.55. Thereby, the answer is simply 0.55. Reflection coefficient is definitely, magnitude part is between 0 and 1. Please check whether the answer what you are getting is within 0 and 1 for your magnitude part. And the range of standing wave ratio, what are the possible values of the standing wave ratio? We have already identified, so it should be within 1 to infinity, so that is C answer is that. Okay, so it is 1 minus R by 1 plus R. Okay, so actually it is 1 plus capital gamma by 1 minus capital gamma. So minimum value is 1, maximum value is infinity. Okay. So for matched line, the standing wave ratio is going to be exactly 1. So the answer must be B. And the maximum impedance of a 50 ohm line with VSWR equal to 3 is, VSWR is given and characteristic impedance of the line is given. So what is the maximum value what we can have? So you can take it as RL by R0 is equal to 3. R0 is 50 ohms. So RL must be 3 into 50. So it should be 150 ohms because it is given as maximum impedance. If you take the other ratio, that is R0 by RL, so you will get the minimum value. So it is again 50 by 3. It should be. Okay, so 50 by 3 is going to give you minimum value, but what is asked is maximum impedance, so it should be 50 into 3, what we are going to take in this case, so that is 150 ohms. So minimum impedance of 75 ohm load with a VSWR of 2.5. So 2.5 is equal to something, so 75 by something. So 75 by 2.5 is what we are going to have, and it is going to be 30 volts, right? So this is how we are going to have various questions depending on the type of exam. And VSWR, transmission line, and reflection coefficient, these are very important ones just to brush up before going for any competitive exam. Okay, and if it is an interview, please be careful. People may have read some vague questions, like what is the range of reflection coefficient, and they expect the answer as 0 to 1. Please remember. So such type of ambiguous things are likely to happen. One must be careful with these calculations. Okay, so this is something on the case of your transmission lines and other calculations. And this is the specific one which is meant for determining the load impedance. Please remember, we are going to measure VSWR value and also measure the distance to the first minimum only. From these two informations, we are going to determine mod gamma value and theta gamma value. The reflection coefficient magnitude and phase will be determined from the measured values of S and Zn prime from this equation, and substituting them in the corresponding final equation, you are going to have Zl value. The impedance is going to be determined. So this is how the next step will be for this. Okay, so let us recapitulate whatever has been discussed so far and what are the different aspects of this. Here we started with the discussions on applications of these transmission lines, as open circuited line and short circuited line can be replacements for capacitors and inductors. A short circuited line can be used as an inductor or a capacitor. An open circuited line can also be used as an inductor or a capacitor, and they can also be used in addition to this as series resonant circuit or shunt resonant circuits. We are not worried about the lengths in general when you are using them in the circuit operations. Whichever one is going to give better performance in terms of inductance and capacitance over a broad range of frequencies and not disturbing the other circuits by radiating these signals. These are the deciding factors, okay, for open circuited line or a short circuited line to be used in a particular system. And the capacitance value will be coming up from an open circuited line if the length is less than lambda by 4, and if the length is greater than lambda by 4, it's going to act like an inductor. Whereas short circuited line, if the length is less than lambda by 4, it's going to act like an inductor, and if the length is greater than lambda by 4, it's going to act like a capacitor. So for the capacitance and inductance effects, you will have lengths less than lambda by 4 or greater than lambda by 4, open circuited line, short circuited line. These are some of the applications. Now, this quarter wave line is a very, very useful one. I mentioned to you about the quarter wave line as copper insulator. It can also be called as copper insulator if the line is short circuited at one end. So because a short circuited transmission line of length quarter wave is going to act like an open circuit or act like a switch. It can be used to stop the current flow in a particular direction. That's why it is switch or a copper insulator. It insulates the power. So though a connection appears, it is actually not allowing the power to go because of the length. Okay, and that is the speciality of this subject. So copper insulators do exist. So a quarter wave line is generally used to match a specific impedance to another impedance transmission line, because the characteristic impedance of that quarter wave line should be geometric mean between the load impedance value and the impedance to which you want to match. So input impedance here is equal to R0 square by ZL, right? ZL is the load impedance, R0 is your characteristic impedance of the line which you have to choose. The line length is fixed as lambda by 4, but it will have a very narrow band of operation possible because of this, and there are various methods people have used to improve this band or which the characteristic impedance of one value is used to match a load with another type of impedance or a wide range of frequencies. So quarter wave line has huge number of applications in filters and tuning circuits, or in oscillators, amplifiers, and many other places also. Okay, so this is, then a half wave is also discussed. The half wave is going to be for an extension of the transmission line. If you want to connect a load in a particular system, and that load position where you want to add is inaccessible, so we extend the line by half wavelength so that the currents and voltages are not disturbed and you can connect the load at that location. There is no disturbance electrically for the entire system. So half wave lines are used for repeating the load impedance values. So this is one thing, and measurement of this characteristic impedance and gamma is always done through open circuited lines and short circuited lines. That means if a line is given to us and we don't know its characteristic impedance and propagation constant, then what we try to do is we open circuit at one end and measure the input impedance at the other end. Similarly, we short circuit one end and measure the input impedance at the other end. The short circuited and open circuited input impedances measured will give you the characteristic impedance if you take the geometric mean between them, and they will also give you the propagation constant by taking the second expression as shown here, 1 by L tan H inverse square root of ZIS by ZIO. ZIS is when the line is short circuited, what is the input impedance? When the line is open circuited at one end, what is the input impedance? So these are the methods, that is open circuit and short circuit impedances are crucial for all the transmission line works. And in today's class, we have also come across a new parameter, that is the reflection coefficient, which is a complex quantity and which is a measure of how much reflection is happening on a particular transmission line due to mismatched load. That is, if the load is matched, there is no reflection at all. All the power that is given from the transmitter will be faithfully transmitted into the load by the transmission line. If the load impedance value is different from characteristic impedance of the line used, then you are going to have a reflected voltage wave traveling from load to the source and giving rise to both the waves, but they are mixed up. The reflected and the incident waves together only will be what you can observe on a transmission line, which is known as a standing wave. So reflection coefficient is a complex quantity which is having amplitude and phase, and the phase of the reflection coefficient changes along the transmission line with a simple equation, a linear equation, y equal to mx plus c type of thing, whereas the amplitude we normally consider to be same all along the transmission line because we use the lines which are very low loss, considering them as lossless lines. So on a lossless line, the magnitude of the reflection coefficient remains the same, whereas the phase changes. So if you do the measurement, as the phase changes, you can't have repeatable values possible. So this measurement of reflection coefficient is quite complicated and repeatability cannot be established. So there are certain issues about that. Particularly in good olden days, people wanted to measure and see how good the reflection is there or a bad situation or what is what. So thereby they wanted to introduce a new parameter called standing wave ratio, which is easily measurable, which is measured at various locations along a transmission line, giving you the same values, or expected to give the same values. And so if you measure at various locations, take an average, your measurement error is very, very less. So these are all the advantages with the standing wave ratio. Again, it is defined as the ratio of the maximum of the standing wave to the minimum of the standing wave. S is 1 plus mod gamma by 1 minus mod gamma is a relation with the reflection coefficient, or mod gamma, if you want to know from the measurement of S, it is given as S minus 1 by S plus 1. So the reflection coefficient and voltage standing wave ratio have ranges. The reflection coefficient range of values possible is -1 to 1. Correspondingly, the voltage standing wave ratio has the range of values possible between 1 and infinity. So these are all different things what we have come across, and using this knowledge we have also developed a method to find the unknown load impedance value from measured values of reflection coefficient and distance to the first minimum. So again, please remember what we have discussed is that reflection coefficient magnitude is obtained from VSWR, which can be measured at various locations because several maxima and several minima exist. But what we have said is the distance to the first minimum, it happens only once. So how do we improve the precision of this? Our repeatability can be established. That's what we'll see in the coming classes, and how repeated measurement of Zn prime is possible and get more accurate theta gamma in the coming classes. Thank you, and today the class is completed. Thank you all.